Okay, let's continue. Last time we talked about the global load vector. There are several types of the applied loadings, and it could be the concentrated load, or they are distributed load. And the distributed load could be the distributed over a curved line, or an area. Okay, so the finite element method is a structural analysis method. So we hope we can treat all these loading types, and in the structural analysis we can always analyze the response of the structures. It includes the displacement, the strains, or the stress inside the structures. Okay, so let's talk about the first type of the loadings, the concentrated loads. Okay, the time to take the screenshot. Okay, if we like to consider the concentrated loads, it is the structures, and it is the concentrated loads. Okay, that's the concentrated loads. And there are two types of the loading conditions we can consider. The first type is the applied at the nodal points. And the second type of the concentrated load, which is applied inside an area, inside an element. Okay, for most finite element package, which most of the time, most of the package, they can consider both types of the loadings. But if you are the structure analysis, and you are the one you like to do the structure analysis, you had better choose the first type, since if the concentrated load, they are applied at the nodal points, then you can get better approximations. So it means the solutions will be more accurate compared to the second type of the loadings. Okay, and also remember, if you are the program user, you have the right to decide which type you can get. Okay, remember, the program user, you can draw the elements, and usually the endpoints of the elements, they are the locations of the nodal points. Okay, so the program user who has the right to determine where to cut the elements, and after you draw the lines of the boundary lines of the elements, also the intersections of the boundary lines, they are the locations for the nodal points. Okay, so since the program user he can determine where to cut the elements. Okay, so if there is a applied loading locations, so you can always draw the element boundary which will fulfill the loading points, which is also a nodal points. Okay, so if the applied loads they are applied at the nodal points, okay, so there is a node number. For the node number I, there are 2 degrees of freedom. Okay, for the plane space analysis, we have 2 degrees of freedom for each nodal point. They are the UI and the VI. Okay, for the UI, it is the nodal displacement along the X direction, and the VI, which is the nodal displacement along the Y directions, and the global coordinates X and Y. Okay, they are determined by the program user also. So for the coordinates and how do we cut the elements, or you can say it is the mesh of the problems. The mesh of the problems include how do we cut the elements, how do we assign the locations of the nodal points, and all these they are included in the mesh of the problems. Also, you heard the automatic mesh. The automatic mesh means sometimes the program can help you to define the cut of the elements, the definitions of all the nodal points. These kind of the techniques, they are called the automatic mesh. Okay, so the mesh or the coordinates X and Y, they are determined by the program user. So if you are the one who can determine all these, so you need to understand which one can give you better solutions. Okay, since we have 2 degrees of freedom for each nodal point, one is the displacement along the X direction, the other one is the displacement along the Y direction. And there are also 2 corresponding nodal loadings for these 2 degrees of freedom. Sometimes we use the PXI and the PYI. Okay, so the PXI and the PYI, they are the loading components for if we got a concentrated load applied at this point. So you can decompose these load vectors into 2 component loadings. Okay, so the PXI, it is the component load along the X direction. The PYI, it is the component load along the Y directions. Okay, so you can always decompose concentrated load into 2 separate component loads. Okay, so if we have the concentrated loads applied at these points, then the corresponding work done by these 2 forces. Okay, remember how do we calculate the work done by the concentrated loads? We need always multiply the concentrated load, for example, the first term, the pxi is the load along the x direction. The ui is the displacement along the same direction. And we need to multiply these two together. Also remember the pxi and the ui, both of them, they are the final values of the loading and the displacements. Since we are doing the static analysis, the static analysis means the accelerations, the velocities which are happen in these structures, they are always negligible. So you can say the accelerations close to zeros, and the velocities, they are also close to zeros. So the requirement for static analysis, it is always the loads must be applied gradually to the structures. So the loads, it is increased from the zero to the final values, and they are increased gradually to the final values. Also the displacement, it is not a sudden move from the original position to the final positions. The UI is also gradually increased from the zero to the final values. Okay, that's why we need always multiply a coefficient 1 divided by 2, 1/2 of the coefficients. You can always see these coefficients whenever we calculate the work done by the applied loadings, or when we calculate the strain energy inside the elements. Okay, so that's the work done by the external loads. And if we calculate the V, it will be the negative pxi times ui minus pyi times vi. Okay. So if we have the concentrated load applied at the nodal point, sometimes we just require the user to input the pxi and the pyi to the program, and we just put the sometimes we will assign the initial values to the load vectors. The initial values of the load vector, usually they are all equal to zeros. So first we need to assign the elements in this load vector, they are all equal to 0. And if the user tells you we have the pxi and the pyi, okay, you just assemble them into the corresponding position. Okay, and most of the time we have the U1, V1, U2, V2. So that's the for most programs, the sequence, the arrange of the nodal displacements, they are arranged. The first two degrees of freedom, they are the U1, the V1. The third and the fourth elements, they are the U2 and the V2. So pxi and the pyi, usually it will go to the 2i minus 1 and the 2 times I. So the pxi will be assembled to the 2i minus 1th element, and the pyi will be assigned, assembled to the 2 times ith element. Okay, since the I represents the number of the nodes, and the px and the pyi, they are the loading components along the x and the y directions. Okay, it's time to take a shot. Okay. Okay, so if the considered concentrated loads, they are applied directly to the nodal points, if you are the one who needs to develop the program, it is much easier to handle these problems. You just get those input data and put them to the correct positions in the load vector. So you finish the work. But if we have the concentrated loads which is applied inside an element, okay, what happens if we have the second situations? If the applied loadings, they are not applied at the nodal points. If the load which is applied inside an element, then the concept to calculate the work done by these loadings, or the potential energy due to the applied loading, the basic concepts, they are still same as the previous one, but right now we need to apply the okay, let's assume the point J, which is inside an element, and the Pxj and the Pyj, again, they are the component loads of these applied loadings. The Pxj, which is the applied loading components along the x direction, and the Pyj, which is the component load along the y directions. Okay, we need to multiply the uj and the vj. Okay, but right now we do not have the directly assume the nodal displacements. So with uj and the vj, they are not the basic unknowns. Okay, since the when we assume the displacement field, we just assume the nodal displacement, and the nodal displacement, they are assumed only for those nodal points, but we will not assume the displacement inside an element. But we can still calculate the displacement inside this element, and usually we will require the users to input okay, so we will require the user to input the xj and the yj, and the xj and the yj, they are the coordinates for the load points, and so we know the xj and the yj. Also, we know the pxj and the pyj. But how can we get the uj and the vj? Okay, remember we do not have the u of xy and the v of xy. Okay, so remember the displacement functions. They are defined in the masked element, and also we use the mapping from the real element to the masked element, and also we have the inverse mapping. The inverse mapping will send the developed x and the y functions and the u and the v functions in the masked element to the real element. Okay, so we have the u of c and eta. We have the v of c and eta, but we do not have the u of xy and the v of xy. Okay, but we have the x of c and eta, y of c and eta. Also, we have the u of c and eta and the v of c and eta. Okay, but we have these two sets of the functions, but we do not have the u of xy and the v of xy. Okay, then how can we find the uj and the vj? And remember what kind of the informations they are, the known information, and what kind of the data we do not have. Okay, it's time to print the screen. Okay, so I will repeat what are the known values. We know the xj and the y. We know the xj and the yj. Also, if we have used the 4 node elements, we know the x1, y1, x2, y2 until the x4, y4. Okay, they are the known values. Okay, so we know all of these. Also, we have the assumed u1, v1. Okay, and they are for these 4. They are the assumed basic unknown. Okay, so we know the xj, yj, we know the x1, y1, x2, y2, and we have the assumed u1, v1, u2, v2 until the u4, v4. And the purpose we like to, how do we get the okay, how can we calculate the uj and the vj? Okay, first we need to find the corresponding locations, the j points. We have that this one is the real element, which is in the xy plane. Also, we have the masked element. Okay, we have the xy plane, and then this one is the real element. Also, we have the masked element, which is the in the c and the eta plane. And first we need to find the corresponding points. Okay, first we need to find the corresponding point of the point J. The point J, it is the point in the real element. But how can we find the point in the mass element? And let's assume these two values, they are the Xc J and the eta J. Okay. If we can find these two coordinates, then the xj will be the summations. Okay, so if we can find the Xc J and the eta J, then by the definitions of the inverse geometric mapping, if we replace the Xc and the eta by the Xc J and the eta J into the shape functions and multiplied by the corresponding x coordinates, which will give you the xj. And again, if we replace the Xc and the eta by the Xc J and the eta J, multiply by the yi, then you can get the yj. And right now we know the xj and the yj. Also we know all of the xi and the yi. And also we know all the shape functions. No matter you use the 4-node element, 9-node element, or 16-node element, the shape functions, they are always can be developed. Okay, but how can we get the Xc J and the eta J? Sometimes for a relatively simple functions, for example, if you consider the 4-node element, sometimes you can solve the inverse functions. So right now we know the x, which is a function of Xc and the eta. So it is easy to, if we know the Xc and the eta, then it is relatively much easier to get the corresponding x and the y, since that's the when we develop the interpolation functions, the shape functions, and since we have these two formulas, so it is not difficult to use the known Xc and the eta to get the corresponding x and the y. So we have these two functions, and sometimes some of the mathematical packages, like the MathCAD or some other package, which can help you to solve the inverse functions. If we can use the package to solve the inverse functions, the inverse functions means the how can we get the Kasi, which is Kasi of x and y, eta. Okay, but they can be solved for some relatively easy functions. If we have only if we use only the 4-node element, the shape functions, they are only the first degree polynomial functions, and totally we got only 4 functions and the 4 xi or 4 yi. So it will be easier to solve the inverse functions. If you solve the inverse functions, then you can replace the x and y by the xj and yj. Then you can find the Cj and the eta j. Okay, but if we got the more nodal points, if we consider the element which use the 9 nodal points or 16 nodal points, then sometimes it is not so easy to find the inverse functions. Okay, so then I will introduce one numerical methods which can help you find the Cj and the eta j. Okay, print the screen. Okay, so it is the numerical method to find the okay. How can we use a numerical procedure to find the Cj and the eta j? It is a trial and error. Okay, so it is a trial and error solution procedure. So first we will try it. First, we will try the Cj and the eta j equal to 0 and 0. And remember, the 0 and the 0, they are the center point. Okay, remember the Cj and the eta, both of them, they are range from the -1 to +1, -1 to +1. So 0 and the 0 will be the center point of the masked element. Okay, it is not the final value of the Cj and the eta j. It is only the first trial point for the Cj and the eta j. So if this one is the trial positions of the Cj and the eta j, then we can calculate the corresponding xj and yj. Okay, so we can calculate if the trial locations for the j point, which is the 0 and the 0, then we can calculate the corresponding xj and yj. But you cannot expect the first trial locations, which is the final, which they are exactly the result point you like to get. So I will add a bar to these two values. The bars means it is only a trial xj and the yj. So usually the xj bar and the yj bar, they are different from the input xj and the yj. Okay, they most of the time they are different. Okay, so print the screen. Okay, so if the xj bar and the yj bar, they are different from the input xj and the yj, then we can calculate the delta x and the delta y. Okay, so we can calculate the difference between the input xj and the yj's and the calculated xj bar and the yj bar. Okay, but remember, most of the time they are different. Also remember, we have the formula dx and the dy. They will be the Jacobi matrix times d c and the d eta. Okay, theoretically, the d c and the d eta, they should be a vector, which is the infinitely small vector. So the length of the d c and the d eta, it should be close to 0. Also, the calculated dx and the dy, the vector in the real element, it is also an infinitely small vector. So the length of the dx and the dy, it is also close to 0. And the Jacobi matrix, which is functions of the c and the eta. If we know the c j and the eta j, although they are the assumed or the trial values of the c j and the eta j, but since we assume the c j and the eta j, so we can calculate the corresponding Jacobi matrix. So at the c j and eta j, we can calculate the Jacobi matrix. And this formula, which is correct for infinitely small vectors of the d c d eta and the dx dy. But right now we have a vector which is much larger than the theoretically infinitely small vector. But we can say this one okay, but we know if the delta x and the delta y, they are we have a certain length for this vector. It is not an infinitely small vector, but however you can add, which is approximated. So the delta x delta y is approximated of this y, and for this formula, which terms they are the known value, which one is the unknown values. Okay, if it is in the classroom, I will ask one of you to answer the questions, but it is online course, so I do not have the chance to ask one of you. Okay, but think about this one first. How many vectors or how many matrices in this formula they are the known ones, and which one or which two they are the unknown ones? Okay, I will give you all of you 10 seconds to consider this problem. Okay, which one is known? This one is known. This one is known. And which one is unknown? Okay, since we can calculate this one, delta x and the delta y can be calculated. And also we have the trial Cj and eta j, so the Jacobi matrix can be calculated. And for the plane stress problems, the Jacobi matrix, which is a 2x2 matrix, and the delta x, delta y, it is a 2x1 vector. And the delta Cc and the delta eta, it is also a 2x1 vector. So actually it is a simultaneous equations problems. Right now we have two equations and with two unknowns. And you can solve these two equations to get the delta Cc and the delta eta. Okay, so we can solve these two equations to get the delta Cc and the delta eta. After we solve the delta Cc and the delta eta, then we can get the second trial Cc. Okay, the originally assumed Cj and eta j, they are equal to 0 and 0. And after we solve the delta Cc and the delta eta, then we can get a new trial value, and which is the Cj and the eta j. Okay, so we will not finish the iterations after this one. Usually you need to go to the third iteration, or sometimes even you need to go to the fourth or the fifth iterations until the delta Cc and the delta eta, they are both equal, they are both close to zeros. So it means as long as the difference of the two trial points, they are very, very close. So then you can finish the iterations. If you do not accept the delta Cc and the delta eta, then you need to continue to the next iterations. So we can iterate to get the final Cj and the eta j. Okay. So print the screen. Okay. Okay. So if we solve the Cj and the eta j, then we can get okay, after we solve the Cj and the eta j, then we can calculate the uj and the vj. Okay, so since we have the assumed nodal displacements u1 v1 until the u4 v4, and after we solve the Cj and the eta j, then the corresponding point, the displacements uj and the vj, we can use previous formula to calculate the uj and the vj. Okay, so we use the assumed displacement functions. Also, we can calculate any point inside this element. We can calculate their displacements. After these two have been assumed, have been calculated, then what will be the work done by this force? Okay, if we like to calculate the work done by the concentrated load applied at the point J, then we need to multiply the corresponding displacements uj and vj by the two applied loading components psj and pyj. If we multiply these two together and divide it by them by the two, then we can get the work done by this force. And the uj and the vj, they are the equal to the vector transpose. And what is the uj and the vj? Okay, uj and vj, if we use these two formula and write them in the matrix form, it will be this 2 by 8 matrix multiplied by the 8 by 1 vector. And sometimes we can say this one is the n vector times u displacement. Okay, so the n will be the 2 by 8. This one is 8 by 1. Since the right now I have assumed we got four. It is a 4-node element. So if this element is a 4-node element, then the total number of the unknowns related to this element will be the u1 v1 until the u4 v4. Okay, so uj and the vj, they are equal to the n multiplied by the u. So the uj and the vj transpose will be the u transpose times n transpose. The uj and the vj transpose will be the u transpose times the n transpose. And this one will be 1 by 8. This one is 8 by 2. This one is 8 by 2. And the work will be the 1/2 u transpose times n transpose times pxj pyj. Okay, this one is the 1 by 8, 8 by 2, 2 by 1. Okay. And sometimes we will multiply the second and the third matrix. If we multiply these two together, it will be a vector which is 8 by 1. And this 8 by 1 vector, sometimes it is called the equivalent load vector. Okay, sometimes the if we multiply the n transpose by the pxj and the pyj, then you can get a vector. And in this vector, there are 8 elements. And also this vector is called the equivalent load vector. Why it is called the equivalent load vector? Since the this will p vector. Okay, and theoretically, one concentrated load P, xj, and pyj applied to the point j, the work done by this set of the loading and the corresponding displacements, the work done by this set of the loadings will be same as the work done by there are 4 nodal points, and there are totally 8 concentrated load applied to 4 different points. And since we have the 8 different component loadings, and the loads must be applied, must be multiplied by the corresponding nodal displacements. But however, the work done by if this one is the W1, this one is W2. The work done by these 2 sets of the loadings, they are equal. So that's why it is called the equivalent load vector. Sometimes it is called the equivalent work load vector. So theoretically, the work done by these 2 sets, they are same. They are same. Okay, print the screen, and I will finish the second hour of this lesson.